Converting between rectangular and polar equations. So we've done some converting with rectangular and polar coordinates. What about equations themselves? What if you wanted to switch forms? Well, those same relationships that we used before apply here as well. Let's take a look. I've got a couple of rectangular equations here, xy equations, and I want to rewrite them in their equivalent polar form. In other words, I want to change to r and theta. It's all about using the relationships in that box. Letter A, x squared plus y squared equals 25. Now hopefully you recognize that. That is the equation of a circle in the xy plane. It would be centered at 0, 0 with a radius of 5, right? The square root of 25 gives the radius. To convert it to polar form, well, this one's pretty simple. I can see that x squared plus y squared is interchangeable with r squared. And so just like that, I've replaced x and y with r. I can simplify this further by square rooting both sides. Normally I would have a plus or minus there, but walking forward 5 steps in every direction and walking backwards 5 steps in every direction, those are all the same points, so that's unnecessary. The simplest version of this polar equation is r equals 5. In fact, you might remember we've already concluded that equations in the form r equals a number represent circles. Notice that the polar form of this equation is much, much simpler than the rectangular form. That becomes important later on in calculus, where sometimes we'll switch a problem into polar form to make the calculus work a little bit easier. Let's take a look at letter B. I have the equation y equals 4. This is a simple rectangular equation. It's the graph of a horizontal line where all the y coordinates are 4. Well, what if I wanted to switch this over into polar form? It looks like this equation here would be useful to me because I can simply replace y with r sine theta, and again, just like that, no more x's and y's, only r's and thetas. Where possible, we prefer to solve the equations for r. So this would typically get written r equals 4 over sine theta, and that's probably fine. Or I could write it without any fractions by reciprocating that sine theta to the top. That would turn it into a cosecant theta, the reciprocal of the sine function. This is probably the simplest, shortest way to write the equation in polar form. Now, going the other direction, where you're switching from polar form into rectangular form, can be a little bit more difficult. You have to learn some tricks along the way. Let's take a look at these two examples. The first one is r equals 4 sine theta. I want to get rid of the r's and thetas and have only x's and y's. Of course, I'm looking over here and I don't really see an r by itself. I wish I had an r squared. Well, I could accomplish that by multiplying this r by another copy of r. If I do that on the left, I'll have to do that on the right. Oh wait, that'll help me there as well because I don't really want to have a sine theta by itself. I want to have an r sine theta. That's a very common trick in these problems. Multiply both sides by r. This becomes r squared. This becomes 4r sine theta. Now the conversion is easy. R squared, same thing as x squared plus y squared. R sine theta, that is equal to y. Here is the simplest form of that rectangular equation. By the way, just as a side note, you might recognize this is also a circle from algebra. It's not quite in the normal form for circles. What I would have to do to put it in that form is move the 4y to the other side, and then this piece here I would have to complete the square. I would have to turn it into a perfect square by taking that negative 4, cutting it in half, negative 2, and squaring it, which makes a positive 4. If I add 4 there, I got to add 4 here. Again, I'm recalling some algebra knowledge for you. Now that perfect square factors as y minus 2 squared. You can FOIL that out and verify it. The minus 2 was that cut in half number that we used. The right side is 4. So to put that equation in normal circle form, that's what I would do. This is the circle with a center of 0, 2. That's the impact of that y minus 2 term. And the radius of the circle would be the square root of 4, which is 2. Now, this last part is probably only useful if I needed to draw a graph of the equation. In terms of just converting to rectangular form, this version is just fine, if not a little bit simpler. The last example says r equals 3, and you might think, oh, we should do that same trick. Let's just multiply both sides by r, then I'll have an r squared. Yeah, but then on the other side, I'd have a 3r. I'd have another r by itself, so that's not really going to help. The trick here is a little bit different. Instead of multiplying both sides by r, I'll square both sides, which is another legal algebra move. And that will give me r squared equals 9. Then the r squared can be replaced with x squared plus y squared, and just like that, I'm finished. Here's the rectangular version, the rectangular form of that polar equation. That is a circle centered at 0, 0 with radius 3. This should not be surprising to you. We have already learned that r equals 3 generates a circle. Thanks for watching.